Hi there, welcome to lecture 17 of FOCS. We're going to be talking about independence, which is an assumption that sometimes we can make that simplifies the computation of probabilities. But as usual, before we get going, let's quickly recap what we did last time. Okay, last time we were talking about conditional probability. So this is a very important topic. It's how do you update your probability when new information arrives? And it's very important to always be, taking into account all the information that's available about the experiment so that you can compute the correct probability, the correct chances of whatever you're interested in happening. Okay, so we developed, just like computing probabilities, computing conditional probabilities reduces to computing probabilities, and so you can, mechanically compute the probabilities based on the sort of definition, and then the interpretation is that it's the updated probability to take into account the new information. Now, conditional probability is subtle, and it's possible to fall into several, different types of, traps, conditional probability traps. We talked about sampling bias, we talked about the transposed conditional using probability of B given A instead of the probability of A given B, and its application to medical testing. Okay, and then we ended last lecture with a very simple principle, the law of total probability. It's a simple principle. It says, it gives the formula for how you can break down an event A into two events and then sort of add up weighted, probabilities to get the probability of A. This law of total probability is simple, but it is very important. Okay? It's sort of a case-by-case analysis, technique for probability. And, we can use it for build-up probability, just like build-up counting. We can use it to simplify the analysis of, computing probabilities when things can go on forever, if they repeat. And we can also use it to just compute the probability of more complex events. Okay? So that's conditional probability. Make sure you read the chapter carefully. I mean, it's a very important chapter. Lots of problems, lots of exercises, lots of pop quizzes. Do them. Okay? And today we're going to be talking about independence. Okay? And I want to emphasize that, independence is not a theorem or an axiom. It's an assumption. Some experiments you can assume independence. In some experiments you cannot. Okay? And now we'll talk about various applications of independence. Starting with the Fermi-method, which is a very good technique for, approximating things. Okay, and then we'll talk about the birthday paradox, which has an application to one of the most famous algorithms in computer science, hashing. Without hashing, lots of practical applications just would take too long. Okay, and then we're going to talk about the random walk, okay, and the gambler's ruin problem. And you definitely want to avoid the gambler's ruin. Okay, so let's move to the board and get going. Okay, independence. And I want to emphasize that independence is an assumption. So you cannot assume it in general for whatever problem you're working on. Okay, so independence. Okay, it's an assumption. And sometimes it holds and sometimes it doesn't. But when it does hold, computing probabilities can be much easier. So let's talk about what independence is. You're interested in two things, and these two things have nothing to do with each other. So what does that mean? Let's pin it down. Okay, so you have consider two kids. Okay, from the same two parents. Okay, and the first is a girl. First is a girl. Okay, what's the second, a boy or a girl? So you should be looking at me and saying, how would I know? Okay, and that's key to independence. So telling you that the first is a girl tells you nothing about whether or not the second is a girl. And that's the prevailing medical opinion, that the sexes of children, even within the same family, they're independent. Okay, so sexes of kids are independent. Okay, that's what we mean by have nothing to do with each other. If I tell you something about the first thing you're interested in, it doesn't tell you anything about the second. Let's take another example, eye color. Okay, so the girl has blue eyes. What about the second kid? Does the second kid have blue eyes or not? And now you might think, I'm going to guess that the second kid has blue eyes. Why? Because if the girl has blue eyes, probably the parents have blue eyes and eye color is inherited. And so that suggests that the second kid also might have blue eyes. So key difference from the sex of the kids, boy or girl. Key difference. Okay. Eye color of the first child tells you something about the eye color of the second child. So eye color is not independent, even for kids in the same family. But the eye color of one kid in one family might be independent of the eye color of some other kid in some other family. So if I told you that, this girl has blue eyes, what are the colors of the children in my family? You'd look at me and say, oh, that doesn't give me any information. Okay? But in this case, eye color for kids in the same family, not independent. So now you see that independence is sort of a phenomenon that may or may not hold. That's why we say it's an assumption. Let's take another example. Flip 2 coins. So you flip the 2 coins. The first flips heads. Okay, so what's the second flip? Look at me and say, how would I know? That's the key to independence. So telling you something about the first coin flip tells you nothing about what the second coin flipped. Okay, and so the 2 coin flips are independent. Okay, so the 2 coin flips are independent. Okay, and usually, and we'll do lots of experiments with coins, and so we will typically say something like, you have 10 coins, assume that they're all independent. Okay, so you flip 10 independent coins. That means that whenever you flip one of them, it tells you nothing about the others. Okay, one more, last example. Okay, it's raining today, so we're interested in days where it rains and days where it's cloudy. So today's a rainy day. Today, okay, it's rainy. Okay, so I'm now interested in whether or not there are clouds. Question mark. Are there clouds? Look at me and say, yes, of course. Okay, because that's the way the world works. It can only rain if there are clouds. And so that what that tells you is that whether or not a day is rainy and whether or not a day is cloudy are not independent, because telling you something about one gives you an idea what's going on with the other. Not independent. Okay, so now let's mathematically pin this down. Okay, so let's take the case of 2 coin flips, which are independent. So independent coin flips. Okay, now we argued that they're independent intuitively on the basis that one flip doesn't tell you about another, but let's see what happens when you do the 2 coin flips. And let's say you do it 100 times. Okay, so you flip 100 times. The first coin will be heads roughly 50 times. Okay, that's what it means for the probability of, well, let's assume the coins are fair. That's what it means for the probability of heads to be 1/2. Okay, and now what's going on with the second flip? Okay, and the second coin, so 50 of them are heads, 50 of them are tails. Okay, and the second coin, says, I don't care what happened to the first coin. I'm going to behave independently. So no matter what whether the first coin was heads or tails, in either case, for these 50, roughly 25 will be heads, tails, and roughly 25 will be heads, tails. And we could ask, how many of these experiments came up heads? So coin 1 heads for coin 1. Let's write that as coin 1 heads and coin 2 heads. Okay. How many times does that happen? Is 25 times, and if we take the frequency interpretation of probability, 25 over 100 is, the probability that you get coin 1 heads and coin 2 heads, which is, 1/4. Okay. And then when we did the mechanical approach to probability, we said we're going to take, we put edge probabilities 1/4, 1/2, 1/2, and 1/2, and so on all the edges, and then we multiply the edge probabilities to get the outcome probability. So 1/2 times 1/2 is 1/4. So this is 1/2 times 1/2. So we get the probability of coin 1 heads and coin 2 heads is 1/2 times 1/2. But we observe that this is the probability of coin 1 head, and this is the probability of coin 2 head. Okay, and you're multiplying these two probabilities and you get the probability of coin 1 head and coin 2 head. And it turns out that, this notion of the and of the two outcomes is key to the definition of, the mathematical definition of independence. Okay, so now let's look at a situation where we didn't have independence. Let's say we look at, rainy and cloudy days. So not independent. Okay, so let's look at the chances of a rainy and a cloudy day. Probability of rainy and clouds. Okay, well, we did this last time. That's the intersection of the rainy days and the cloudy days. But every rainy day is cloudy. So this is, rain, intersection clouds. And this is equal to rain. Because every rainy day is cloudy. So this is just the probability of a rainy day. Okay, which is, where when we talked last time, we said that it's cloudy 1 in 7 days and it's raining it's cloudy 1 in 5 days and it's raining 1 in 7 days. Okay, so the probability of rain is just 1 in 7, which is also the probability of rain and clouds, but this is not equal to the probability of clouds times the probability of rain. It's not equal to 1/5 times 1/7, which is the probability of clouds times the probability of rain. Okay. And so we see in this situation where you do not have independence, the probability of the and is not the product. When you do have independence, the probability of the and is the product. And that ultimately is the fundamental definition of independence. But let's now pin it down in a more general setting. Okay. So, in a more general setting, you have your sample space, you have your experiment, for which you have a sample space and probabilities for each outcome. And so you can define two events, A and B. So you have events A and B, arbitrary events. Okay, and now let's see. A and B are independent. We say A and B are independent. Okay, now let's try to pin this down mathematically. If, knowing that B occurs tells you nothing about whether or not A occurs. Okay, so knowing that B occurs tells you nothing about whether A occurs. Okay, so if I tell you that B occurred, okay, thank you very much. If I tell you that the first child is a girl, well, thank you very much. It tells me nothing about the second child. Okay, what are the chances the second child is a boy? Still a half. If you think of getting children as flipping coins, and each child is equally likely to be either boy or a girl, heads or tails. Okay, so knowing that B occurs tells you nothing about whether or not A occurs. And now in the world of probability, that means that, initially there's some probability that A occurs. Okay, now I tell you that B occurs. That means I give you new information. And did that change the probability that A occurs? No. Okay, so that's the idea behind independent. And now we have a language for that, in the language of conditional probability. So we're saying that probability that A occurs, given some information about B, given that B occurs, does not change the probability that A occurs. So this is the probability that A occurs. It's not changed. Okay, and then we say that A and B are independent. That's the definition of independence. Now you might say, well, we talked about, the AND event multiplying probabilities. I claim that is equivalent to the statement that the probability of A and B occurring is the product of the probability. So let's prove that. Okay. Remember, the probability of A given B is equal to the probability of A and B divided by the probability of B. Well, that's what we said. Okay, we said that the probability, that's the definition of the conditional probability, the probability of A given new information. But now we're saying that when we have independence, so it's an assumption, it doesn't always hold. When we have independence, this guy is equal to the probability of A. So this guy is equal to the probability of A. Now let's just rearrange terms, and you see that we get that the probability of A and B is equal to the probability of A times the probability of B. Okay, so I'm going to box this. And I'm going to box this. Okay, so there you go. When you have independent events, knowing that one occurs doesn't change the probability of the other. That's what this says. Okay, and it is equivalent to saying that the probability that the two events occur, the probability that A and B occurs, is the product of the individual probabilities. Okay, so when you have independence, probabilities multiply when you're computing an AND. And that makes it sometimes very convenient to compute the probabilities of very complicated events. For example, probability that this happens, and that happens, and that happens, and that happens. Well, if they're independent, it's just the product of the individual probabilities. Okay, so let's erase and do lots of examples. Oh no, we dropped it. Okay, let's do an example and then I'll show you an interesting application of independence. Okay, so flip 3 coins. So the outcomes are H, 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 HHT, HT, HTT, THH, THT, TTH, TTT. Okay, so we're constructing the outcome space, and you can do the outcome tree and figure out that it's a uniform probability space, and the probabilities are all 1/8. Okay, so this is flip 3 coins. Okay, now I'm going to define 3 events: A1, A2, and A3. Okay, this is the event coin 1 and 2 match, coin 2 and 3 match, and this is A3 is the event coin 1 and 3 match. Okay, now formally as subsets of the sample space, so coin 1 and 2 match means that they either are both H, okay, so HHH, HHT, or they're both T, TTH, TTT. So there are 4 outcomes, okay, and the similar thing for event A2, coins 2 and 3 match, so you have HHH, THH, HTT, TTT, and coins 1 and 3 match. So HHH, HTH, THT, TTT. And we can ask what's the probability of A1, and that's the same as the probability of A2, and that's the same as the probability of A3. Okay, and because we're in a uniform sample space, we just take the size of the event and divide by the size of the sample space. So this is 4/8, which is 1/2. Okay, and now let's ask for some AND events. So the probability of A1 and A2 is equal to, well, we need to take the intersection. The intersection is the probability of the intersection is just HHH and TTT, the outcomes that are common, HHH and TTT. Okay, and so that's equal to 2/8 equals 1/4. And look, that's equal to the probability of A1 times the probability of A2. Because each of those have probability 1/2. So this is 1/2 times 1/2, which is the product of the probabilities. So A1 and A2 are independent. A1, A2 are independent. Okay, good. Now, you can do the same thing for A1 and A1 and A3, A2 and A3. So probability of A1 and A3 also equals 1/4. And probability of A1, A2, and A3 also equals 1/4. Okay, but now let's consider the intersection, the AND of all 3 events. Probability of A1 and A2 and A3 is equal to, okay, so we need the intersection of all 3 events. And you'll see that it's HHH and TTT is common to all 3 events. So it's the probability of the event HHH and TTT, which is the same as, what we just computed, 2/8. So this is 2/8, which is 1/4. Okay, but the probability of each individual event is 1/2, 1/2, 1/2. If you take the product of these 3, you get 1/8, not 1/4. So this is not equal to the probability of A1 times the probability of A2 times the probability of A3. Okay, and so that's interesting. So here's a situation of 3 events where any pair of them are independent, but the 3 of them taken together are not independent. Okay, and that's possible. It's even possible to find a situation where the 3 of them taken together are independent. So the probability of the AND of 3 events is the product, but then pairwise they are not independent, and you can see the text for that. Now, if you have n events, for example, 3 events or 5 or 10, we say that those events are independent if they are pairwise independent, 3-way independent, 4-way independent, and so on up to n-way independent. In other words, the probability of any AND is the product of the individual probabilities. Okay, so that's an example of independence, 2-way independence, not 3-way independent. Okay, we'll come back. Let's do an application of independence, a very interesting application. Okay, so one powerful application of independence is to estimating things, estimation. Okay.
And we're going to talk about something that could be called a Fermi-method. Okay, some people refer to it as a Fermi-method. It's named after this famous physicist, Enrico Fermi, who was famous, who was very good at estimating all kinds of complex things very quickly. Okay. And one time there was an explosion some distance away, and he threw up a piece of paper, watched how it moved because of the explosion, and estimated the power of the explosion, the yield. Quite fantastic, right? Okay, so, it's very useful to be able to estimate things quickly. That way you can figure out what's going on quickly. Okay. And more practically, you're all CS majors, you sooner or later go to a CS interview, and, sometimes they will ask you in a CS interview, estimate something. Okay. So, for example, what's the circumference of the Earth? And you might think, how would I know that? That's such an esoteric piece of information. Yes, it's esoteric. They don't want you to know that. What they want to see is how do you behave when you don't know something? That's what's interesting. That's what they want to know. How do you behave when you don't know something? And one way to behave when you don't know something, try to estimate. Okay, get good at estimating. So, for example, the circumference of the Earth, you might argue as follows. From the East Coast to the West Coast is about 3,000 miles. That's 3 time zones. The Earth has 24 time zones because it takes 24 hours for the Earth to rotate around once. Okay? So 3 time zones is 3,000 miles. 24 time zones, 24,000 miles. Boom, that's actually a pretty good estimate. So get good at estimating. You won't regret it. Okay. Now, we're going to address a particular problem. Okay. So Paul Drake, another physicist, was interested in how many alien civilizations. Okay. So he basically developed a method, that kind of uses independence, okay, and got a number. And then Peter Backus was interested in how many people are there for me to date. So rather than how many alien civilizations out there, which is of absolutely no use to Peter Backus, he thought, how many dateable girls are there out there for me? Okay. And he wanted to know, what are the chances that he will be able to find a date? Okay. So there's this complex object called a dateable girl, or more generally just dateable. Okay. So dateable. Okay. And the way he approaches this problem is he says, well, dateable means a bunch of things. Okay, so let me see if I can list out the things that dateable means, and they're all reasonable things. And then let's see how we can compute the number of dateable girls. Okay, so probability. He's interested in if I picked a random person from the 7 billion people on Earth, what are the chances that that person will be dateable? Okay, and now you can play this game. For whoever you are, I'm going to play this game. For a typical heterosexual, let's say male, in between the ages of, let's say, 20 to 30, but you can play this game that I'm about to play for yourself, for anybody. Okay. So he says, well, let's identify a dateable person as satisfying certain criteria. Okay. You can think of that as events. So a criterion is satisfied if I picked a random person and they satisfy my criteria. So what collection of people satisfy my criteria? That's an event. Okay, so we'll define some events, and he defined 8 criteria. So let's call them A1, A2, A3, A4, A5, A6, A7, A8. And let me just tell you what those criteria are, and you'll see that they're very reasonable criteria. Okay, so A1, to be dateable, okay, you have to live nearby. Okay. Makes sense, right? If you're dateable, I should be able to go on a date with you, so you live nearby. Okay, if you're dateable, you should be the right sex. Everyone has a preference. Okay, so whatever your preference is, I'm only going to date you if you satisfy my preference. To be dateable, you should have the right age. Again, everyone has a preference, and if to be dateable, you should be single. So this is highly recommended. If you're going to go out on a date, it's highly preferable for the person you're dating to be single. Okay, to be dateable, you should be educated. Okay. Now, we're all RPI students here, so we're all educated, and we like to date people who are educated. To be dateable, I must be attracted to you. So you should be attractive. Okay, and for the dating scenario to be working, for you to be dateable by me, I must be attractive to you. So I must be attractive. And one final condition, if we're going to be able to go on a date, we must get along. That's also a nice thing. So on the one hand, we've got physical attractiveness, and on the other hand, we have personality attractiveness. So we must get along. Okay, and here's the thing. Okay. What Peter Backus said is, well, if you're going to be dateable, then you must have all of these, criteria. And that's why it's so hard to find dateable people, because they have to satisfy all these criteria. You can think of these as deal breakers. Deal breakers. So probability of dateable is the probability of A1 and A2 and so on and A8. That's a tough set of criteria. Now each individual one of them is not so tough, but when you require all of these, now it's getting tough. Okay. Now how are we going to compute this probability? So what basically Paul Drake said is, for example, an alien civilization out there, way out there in the far, universe, you require a planet with water at the right temperature, and so on and so forth. So just like criteria for being dateable, there's got to be a criterion for life to, evolve, and then the materials must be there to build technology, and so on and so forth. Okay. Now, so if we're going to use independence, and this is where independence comes in, you can, roughly speaking, believe that all these criteria are independent. If you picked a random person, there's some chance that they live nearby. And if I told you they live nearby, I'm not telling you anything about their sex or their age. If I tell you where they live and their sex, you don't know about their age. Okay, you don't know whether they're single. Okay, now modulo some minor corrections, like probably if I tell you where they live and it's an urban area, they're less likely to be young, more likely to be old. If it's an urban area, or if it's a metropolitan area like New York City, then they're more likely to be single, maybe. I don't know. And suburban area is more likely to not be single, and so on and so forth. But okay, those are minor dependencies. These quantities don't inform each other. If I tell you you're single, does it say anything about educated? Nope. Does it say anything about attractive? No. Does it say anything about whether or not I'll be attractive to you? Nope. Okay. Does it say anything about we get along? Probably not. Okay. And so we can treat these criteria as more or less independent. Okay. And then what does independence say? Well, we can analyze this complex concept of being dateable by taking this and setting it equal to the product of the individual probabilities. So the probability of dateable is equal to the probability of A1 times the probability of A2 times times the probability of A8. Okay. This is where we use the assumption of independence. Okay. That's why independence makes such calculations of complex things like are you dateable much easier. Okay, so now does that help us? And it's going to help us because I can actually estimate each of these individual probabilities reasonably accurately, whereas this complex thing I have no handle on it from the beginning. Okay, if you ask me, analyze this, it's complex. These guys, these individual conditions that I require, much easier to handle. Okay, so let's see. Lives nearby. Maybe we say that we're in New York State, so you must live in New York State. Okay, so the probability of A1 is equal to, since we're in a uniform probability space, each person is equally likely to be the outcome of a random selection. So it's the number of people who live nearby. So New York State has 20 million people, and the world has 7 billion people. So this is approximately equal to 3 over 1,000. Okay. Right sex. So the probability of A2, there are roughly 50% of each sex. So, take your pick. It's going to be about 1/2. So this is about 1/2 chances of the random person having the right sex. Right age. So we can say if you're around 25, right age is from 20 to 30. So this is the probability that 20 less equal to age less equal to 30. And from the U.S. Census, this is about 15% or 15 over 100. So this is U.S. Census. So sometimes we have to use data. Okay. Probability to be single, roughly 50% of people are single. So probability of A4. This is probability of A3. Probability of A4 is about 1/2. Okay, educated. In the US, about 25% of people have a college degree. So probability of A5. Let's say that if you randomly pick the person, it's approximately 1 in 4 are educated. Probability of attractive. Now you have to sit down and think. How likely, if you pick a random person, am I going to be attracted to them? So you could sit and do this experiment. Sit on the street, every time a person goes by, say attractive, not attractive, attractive, not attractive, and estimate this ratio. That would be a very creepy thing to do, and odds are you would be put in jail. Okay, if you start shouting as everyone passes you, attractive, not attractive, attractive, not attractive, and so on. But we might be able to estimate this. So this is something. This is introspection. You tell me what are the chances you find someone attractive? Maybe 1 in 5. Is approximately 1 in 5. Okay. the seventh criterion, I must be attractive. Now again, this is introspection, and how highly do you think of yourself? Some people might put 1. I'm attractive to everyone. I'm well built and so on. I'm the classic model. Okay, but if you're a little bit more modest, you might say, well, probability of A7, you might set it at 1/5, or even if you're even more modest, you might set it at 1/10. So you don't consider yourself that attractive. Okay, but maybe you do. Who knows? Okay. So you can fill in those numbers. That's the point. Okay. Probability you get along. Maybe you get along with 1 in 4 people, and 3 in 4 people irritate the heck out of you. And maybe the same thing is for the other person, that you are personable to 1 in 4 people, with a probability 1 in 4 to someone else. So 1 in 4 times 1 in 4, the probability that you both get along is about 1 in 16. Probability of A8 is approximately 1 in 16. Okay, but that's all we have to do, because now we can just multiply. This is equal to 3 over 1,000 times 1/2 times 15 over 100 times 1/2 times 1/4 times 1/5 times 1/10 times 1/16. Wow, lots of multiplications. Okay, and if you compute this number, it's approximately equal to 3.5 times 10 to the minus 8, or approximately 1 in 30 million. Wow. And this is the conclusion that Peter Backus somewhat came up with. Wow, it's so hard for me to find someone dateable. That shows you how hard it is to find dateable people. Okay, and if there are 7 billion people, this is approximately equal to 250, okay, which is about 40 or 50 times less than the number of alien civilizations that Paul Drake found. So look at this. The number of dateable people is 40 times less than alien civilizations. That's how hard it is to date. So these 250 precious dateable people, it's a precious resource. Treat it carefully. Okay. Now, the point here is that we take a complex concept and we can estimate how many dateable people there are by using independence. And you might wonder, how accurate is this? Well, it turns out to be quite accurate. Well, first of all, because, these criteria, these deal breakers are more or less independent. And second of all, you might say, but, these were very rough estimates. Yes, that's the idea. There are many criteria. All of them have rough estimates. Some of them will be overestimates. Some of them will be underestimates. And when you multiply them all together, the overestimates cancel out with the underestimates, give you a good approximation. Okay? And you can also see from the nature of independence, that it's multiplicative. So the more deal breakers you have, the more terms will multiply, and this number will get smaller and smaller. So if you have more deal breakers, you're less flexible. You have so many criteria. Okay, this number can drop to 1 or even less than 1. You're in trouble. Okay, so if you find that you have too many deal breakers, you need to become a little more flexible so that this number can, 250 is reasonable. If you can get this up to, let's say, 5,000, you're in good shape. 5,000 dateable people. One way to get this up to, let's say, 5,000, 10,000 is to be a little bit more flexible with geography. Are you willing to move states? Well, maybe not for dating, but ultimately for settling down. Okay, and so on and so forth. Are you willing to have someone who's not educated? Okay. Are you willing to have someone who's less attractive so you can increase this? Are you go and work out so that you can increase that number, and so on and so forth. You can try to increase the 250. Okay. The point is that independence allows you to analyze little conditions and get approximate probabilities, and the approximations balance each other out. Okay. So let's erase. We'll come back and we will talk about FOCS-twins. Wow. Okay, FOCS-twins. Now, pay attention, because this is going to lead us ultimately to a very important popular algorithm in computer science with very important, impact on practice. Okay. Now, every year when I teach this class, I pick a random student. Let's call that student S1. And I ask, what's your birthday? And then I see if someone in the class matches that birthday. And if so, I say we've identified a FOCS-twin. Okay, so FOCS-twins are students with matching birthday. Okay, those are FOCS-twins. And one year, I haven't taught this class that many times, but one year, when I picked the student, boom! Someone had a matching birthday, and we said, yippee! And we were all thrilled because, this looks like some kind of magical miracle. It's like an extreme coincidence. Right? How likely is it? I pick a random student, and someone in the class of approximately 200 students has a matching birthday. Okay? But on some years, I fail. And if I fail, then I'll go to the second student. I'll pick another second random student and ask, what's your birthday, and see if there's a FOCS-twin. And if I fail, I'll pick a third and a fourth and a fifth. So I might go to, student 3, student 4, student 5, Maybe I'll go to student 10. And if I fail, I might keep failing and go to student 25. I might keep failing and go to student 100. And we're wondering, wow, this could be a very tedious class. It turns out, that I've never had to go beyond student 5, in order to find a FOCS-twin. And if I had to go beyond student 10, I would be utterly surprised. So now let's see why. Let's analyze this peculiar coincidence. And we will show that it is actually reasonably likely that I will succeed on student 1. It's a super coincidence, but it looks like a super coincidence, but it's reasonably likely that I will succeed. So let's analyze this phenomenon. So imagine that I define the events, So I'm going to ask students. So I'm going to define the event A1. When I pick the first student, is the event student 1 has no FOCS-twin. And A2, the event that, student 2 has no FOCS-twin. And let's suppose that there are 200 students, although we could make this argument for n students. So AN, AN is the event that student S200. So S200 has no FOCS-twin. And what's going on here? So let's analyze these events. So let's, for example, consider what's the probability that the first student has no FOCS-twin, that A1 occurs. What's the probability of A1 occurring? So let's draw a picture of what's going on. So imagine that I list the birthdays, and rather than call the days January 1st, January 2nd, and so on, I'm going to be very boring and just call the birthdays 1, 2, 3 up to B. So the birthdays are 1, 2, 3, 4, and so on up to birthday B. And B is 366. And we're interested in the situation where the student S1 has no FOCS-twin. So let us assume now, since we're talking about birthdays. So if I pick a random student of my 200 students, and look at their birthday, the outcome is the birthday. So there are B outcomes, and I'm going to assume that all possible birthdays are equally likely. So it's a uniform probability space. So let's make the assumption that all birthdays are equally likely. And we'll make another assumption, and we'll see, what that other assumption is and where we need it. But you should be able to guess what that assumption is because we're talking about independence. We will assume that if you pick two students randomly, and if I tell you, okay, Joe's birthday is, January 19th, and now I picked another student, here's Anna. What's Anna's birthday? You're like, what? How should I know? And the idea here is that, knowing Joe's birthday doesn't tell you anything about Anna's birthday. So the birthdays of students are independent. Birthdays are independent. Now these are both two approximations. Statisticians have studied when are people born, and some days might be more likely than others. It turns out that we can relax that first condition. We don't need it. The chances of finding FOCS-twins are going even higher if all birthdays are not equally likely. As an extreme case, imagine that all people are born on the first day, so only one day is likely. Then I'm guaranteed to find a FOCS-twin by the first student. So all birthdays being equally likely, that just simplifies the analysis. Birthdays are independent is more or less true, except in peculiar situations like, for example, twins. If you have a pair of twins, knowing the birthday of one of them tells you the birthday of the other. So they're not independent. But by and large, birthdays are independent. So now let's analyze the probability that student 1 has no FOCS-twin. So the situation is like this. Student 1 is born on some day, let's say January 9th. But, I can call January 9th day 1. Those are just labels. So we can, some people say, without loss of generality, assume that student 1 is born on day 1. Because he has to be born on some day, and we'll call that day day 1. So now we're asking, what are the chances that student 1 has no FOCS-twin? What that means is that all other students are born on days, 2 up to B. So that's B minus 1 days. So B minus 1 outcomes. So, so student 2 has to be born on day, on days 2 to B, which are B minus 1 outcomes, out of the B outcomes that are equally likely for student 2. So the probability for student 2, to be born on days 2 to B is just equal to B minus 1 divided by B. Okay, because it's a uniform probability space. If I pick, if student 2's birthday is picked uniformly, then the chances of it being in the chances of that outcome being one of these B minus 1 is the number of outcomes that I'm allowing in my event divided by the total number of available outcomes, which is B. And it's the same thing for student 3, and it's the same thing for all students. For example, student 200. They're all, B minus 1 over B, B minus 1 over B. Okay? So all students being born on these B minus 1 days have the same probability, B minus 1 over B. Okay, so the probability that student 2 and student 3 and student 200 are all born on that day is the probability of a big and by independence considerably simplifies this calculation. Okay, by independence, okay, the probability that S2 and S3 and all the way to S200 are born in 2 to B is equal to B minus 1 over B times B minus 1 over B times B minus 1 over B. And that's by independence, because these birthdays are independent. So this is independence. Okay, but this is just B minus 1 over B raised to the power 199. Okay, so let us write that down as the probability that student 1 has no FOCS-twin. So this is equal to B minus 1 over B. Now, if we wanted to, we could say that, well, 199 is just n minus 1, but, for the moment, I'll just keep it as 199. Okay? And if we plug in the numbers, the number of birthdays is 366, so this is 365 over 366 raised to the power 199. Okay? That's the probability that student 1 has no FOCS-twin. Okay? So the chances that student 1 does have a FOCS-twin, if we compute this is approximately 0.58. So the chances of no FOCS-twin is 0.58. So the chances that I succeed with student 1 are approximately 42%. Wow! So it doesn't look like such a miracle anymore, because the first student, my chances are roughly 4 in 10, almost 50% that I will succeed in finding a FOCS-twin. Okay? So it's not that much of a coincidence when you actually sit down and compute the probability. Okay? Now, let's see what's the probability if I fail. Okay, that's the chance. But if I fail, maybe I'll try the second one. So what's the probability that the first and second fail? So probability that S1 has no FOCS-twin and S2 has no FOCS-twin. So probability of A1 and A2. What is that? Okay, so let's analyze that in the same way. Okay, so now, the first student is born on day 1. Okay, now the second student is born on what day? Okay, if both of these guys have no FOCS-twin, then this student cannot be born on day 1. So there are B minus 1 choices for the second student. So this is the probability that, S2 is born on the days 2 to B, and S3 is born S3, S4, all the way up to S200 are not born on the same days. Are not born on days of student 1 and student 2. Okay, so that's the case. That's the situation where both student 1 and student 2 have no FOCS-twin. Student 2 cannot be a FOCS-twin of student 1, and it must be the case that all the other students are not FOCS-twins with either student 1 or student 2. Okay, so this is because these birthdays are independent of this guy. This is the probability that student 2 is born on the days 2 to B. So that's B minus 1 over B. We just computed that probability. There are B minus 1 outcomes available for this guy's birthday. Okay, out of the sample space of B times the probability, okay, that S3 to S200 avoid both these birthdays. Okay, but now, student 2 has to be born on Sunday, let's say September 11th. Okay, and so we might as well, label that day day 2. Okay, so student 2 is born on day 2, and that leaves student 2 up to student 200, b minus 2 days on which they can be born. So each of them will be born on those b minus 2 days with a probability b minus 2 over b, because they have b outcomes in the sample space, and the number of outcomes in the event that we are considering is b minus 2. And since there are 198 of these students, we have to multiply 198 of these by independence. Okay, so this is going to be this raised to the power 198, and that's from independence. And that's also because of independence. So we multiply the two probabilities, and to get this probability, we multiply this probability 198 times for each of the 198 students. Okay? And so this result is b minus 1 over b times b minus 2 over b raised to the power 198. Okay? Okay, so let's write that down. So the chances for me to fail are, fail with students, my first two students is b minus 1 over b times b minus 2 over b raised to the power 198. Good. Okay. Let's do one more case, and then we'll jump to the general situation. So the probability that I fail with my first three students, A1 intersection A2 intersection A3. So students 1, 2, and 3 do not have a FOCS-twin. Okay, same argument. Student 1 is born on day 1. Student 2 has to be born on one of the b minus 1 remaining days. So the chances of that are b minus 1 over b. Student 3 has to be born on one of the b minus 2 remaining days, which we can call day 3. So student 3, whatever it's born on, we can call day 3. But there are b minus 2 choices for student 3. Okay, so we multiply that. Okay, and now there are 197 more students who have available only b minus 3 days in the event that we are interested in. So the chances of that are b minus 3 over b raised to the power 197. There are 197 such students. Okay? And if we continue this argument, the probability of, the first k students not having a FOCS-twin, A1 intersection A2 intersection all the way up to intersection AK. Okay, now you see the pattern. It's going to equal b minus 1 over b times b minus 2 over b times b minus 3 over b, and you have to go all the way up to k, so times b minus k plus 1 over b. Okay, and then the remaining students have to choose among b minus k birthdays. Okay, and how many students are there? 200 minus k. And if we now want to generalize this formula to n students instead of 200, this would just be n. Okay. So you can see that there are two basic parameters, the number of birthdays you have and the number of students you have. And now we're asking, what's the probability that when you pick 1, 2, 3 up to k students, none of them have a FOCS-twin? Okay. So I will box this. Now in our example, n was equal to 200 and b is equal to 366. Okay, so 366 days and 200 students. So let's go ahead and see what are my probabilities. The probability that I succeed by the second student turns out to be approximately 60-odd%. Okay, so it's approximately 66%, 66.3%. The probability of my succeeding by the third student is 80%, 80.4%, 88%. 88.6%, 93%, 93.3%. So the chances are more than 90% that by the time I hit the fifth student, I will have found a FOCS-twin. And if I go to the 10th student, it's 99.5%. And if I go to the 25th student, the chances of failing are basically basically minuscule, 99.999%. 99.999% that I have succeeded by the 25th student. And by the 100th student, basically 100% to numerical precision. So, in practice, you'll never have to go beyond 10. Okay. Now, what about if my class had 367 students? Okay, is it guaranteed that there are FOCS-twins? Yes, but with 200 students, it's not guaranteed that there are FOCS-twins. Okay. So it's possible to completely fail, but the chances of that happening are minuscule, and that's due to the independence and the multiplying of the probability. If there are 367 students, you have to find a FOCS-twin eventually by the pigeonhole principle. Okay, let's do a quick application. Birthday paradox. So a quick application of this, analysis. Okay. Okay, now we analyzed it for FOCS-twins when I pick students one by one in the class, but the typical way in which this is presented is a much simpler setting called the birthday paradox. 50 people are at a party, so 50 people at a party. What are the chances of two people having the same birthday? We can call them party twins. Okay, so chances of party twins. Two people having the same birthday. Okay, so basically you can think of it as the same game we played in FOCS, but you ask the first person, do you have a party twin, second, third, fourth, and you keep going up to the 50th. So we can ask, what are the chances that, all 50 people don't have a party twin? So we want the probability that, student 1 and student 2 and all the way up to student n, which is 50, do not have a party twin. Okay, and we can now just use this formula. It's going to equal, okay, in that specific example, B is still, B is still 366 because we're interested in, birthdays. There are 366 birthdays, and N is now 50. Okay. But K, we're interested in all people not having a twin, so K is equal to N, which is equal to 50. So this is the special case that arises in the birthday paradox. Okay, and so this is equal to 365 over 366 times 364 over 366 times 363 over 366 times ... Okay, so we keep going up to 366 minus 50 plus 1. So 366 minus 50 plus 1 is 317 over 366 times, okay, B minus K, so B minus 50. Excuse me. 366 minus 50 over B, but that's all irrelevant because N equals K, so 50 minus 50 is 0. So this is something to the power 0, which is 1. So times 1. Okay. And if you compute this number, it's approximately equal to 0.03. So the chances of no party twin is 0.03. If you ask the first person, do you have a twin, second, third, fourth, and make it all the way to the 50th, and none of them have a twin, it's exactly this problem as we just described, and 97% chance that you will find a party twin. So chances of party twin equals 97%. Wow! Okay. And that's why it's called a paradox. Okay. In such a small party of 50, the chances are so high that two people will have the same birthday, even though there are 366 birthdays. And that is so surprising a coincidence that it has been called a paradox. But there's no paradox. It's not really a paradox because, when you compute the probability using independence, you get that it is almost for sure that you will find a pair of party twins. Okay, now let's erase, and I'm going to show you the application of this fantastic formula to this very important algorithm in computer science. Let's keep the formula. Okay, so we're going to talk about a very nice application of this whole independence and this birthday/coincidence analysis of FOCS-twins to search and hashing. And there's a pretty big company whose name starts with a G that makes its living off this. This is a very important algorithm in computer science. Now I took the liberty of drawing an example, a concrete example, which we can use to just sort of fix the problem. Okay, so you have 3 web pages, and of course the world has many more. It's a much more challenging problem in practice. But imagine 3 web pages. Page 1 has text, dirty apples hurt health. Page 2, health freaks hate dirty apples. Page 3, survey, people hate bananas. Okay, so you've got some text on various web pages, and now you want to facilitate search queries. So someone might come and put in a query like apples, and you have to, return the search result. Apples appear on page 1, web page 1, and web page 2. So you have to return the result page 1, page 2. Okay. Now, the standard way to solve this problem, and forget about what's going on at the bottom. The standard way to solve this problem might be, it might be what we could call a web address directory, just like a telephone directory. Okay. Take every word, okay, and sort the words. Okay, just like a telephone directory sorts names. So sort the words, okay, and then to each word attach a list of the pages it appears. Okay, so now when you search apples, you find the word apples in your directory, apples, and you return page 1, page 2. If I search the query hate, you find the word hate in your directory, and you return the page. You return the query the search result page 2, page 3. Okay. So the algorithm here is find word in directory. Okay, and return pages. Okay, we can ask, how long is this going to take? So if you have n words, and there are many, 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 many words. So if you have n words, okay, then you have to sort at n words, and now you need to find a word, and we can use binary search. And so we all know that takes order of log n time. So order of log n time search. And that's pretty good. Except that when n is big, log n might be 10, 20, who knows, something like, a reasonably large number of seconds. Okay? And that's not good enough. Humans want instant gratification. So they want order of 1 search time. Okay? We've studied order analysis before, so you know what we mean by order of log n versus order of 1. Constant, instant gratification. So what about constant search time? Okay. So if you want constant search time, then basically the only data structure we really know that gives you more or less constant access to the elements is a table or an array. So now you have to use an array. Okay. And that's what I'm showing here, an array of size 11. Having indexed by 0, 1, 2, up to 10. And so if you store, instead of in a sorted list, instead of storing in a sorted vector, if you store them in a table, then you can instantly jump, for example, to, if you search for hurt, you can instantly jump to table entry 2 and figure out, hurt. As long as you know that hurt is stored in table entry 2. Okay? And that's where hashing comes in. Hashing comes in to give you constant time search. Okay, but you need to first create your table, and you need to have a way of sort of remembering and being able to instantly go to the table row that contains a particular word. Okay, and so here's how hash does it. Okay, so step 1 is we say you hash the words. Hash the words to a hash table. Okay, and what does this is usually what we call a hash function. So there's a hash function that we call it h. Okay, and this hash function takes as input a word. So it's a function. So it takes as input a word and tells you what table will you store the word. Okay, so for example, and the typical types of hash functions are built in the following way. So the hash function, for example, of hate. Okay, so now we need to find a number between 0 and 10 for hate. Okay, so now each letter is given a number. For example, h equals 8, a equals 1, and so on. Okay, so you take each number corresponding to the letter. So in this case, you have the numbers 8, 1, 20 for T, and 5 for E. Okay, and you raise it to some large power, like a large prime power. For example, 17. Add them all together. Okay, but now since you want a number between 0 and 1, you take the remainder modulo 11. So you take the remainder modulo 11. Okay, and this will give me the value 7. And so you see that hate is stored in table row 7. Okay, so you can instead of storing your words in a sorted list, what you do is you take each word, apply your hash function, and it tells you the table row. Now if you want to search, some query, for example, you want to search hurt. Okay. Well, you first compute the hash function of hurt. So you compute hash of hurt, which gives you 2, and that tells you the table row that hurt is stored in. And the nice thing is that this hash function is quick to compute. It's a constant time computation. That's important. Okay. So that takes you to table row 2, and you immediately find hurt, and you return the search result P1, and it's all taking constant time. Okay. Now there's a problem. If you wanted to search hate, so you first hash hate, okay, and that takes you to table row 7. So you go to table row 7, and anyone see the problem? The problem is what you find in table row 7 is not hate, but you find freaks. Actually, the problem is not that you find freaks. The problem is that there are more than 2 words there are more than one word that are stored in table row 7, freaks and hate. So actually what you have to do is you have to come to table row 7, and then if you don't find, you have to find hate here. Okay, so, or it's nowhere. Okay, so you find freaks, you say, oh, that's not hate. So now you go to the next one. Oh, that's hate. Okay, and now that you found hate, you can return the search result, page 1, page 2. Okay? But that's now taking more time, a little more time, but even a little more time is bad. So this is an example of what we call a collision. Okay? So when you search for hate, you see there's a collision. So two or more words are stored in the same table row. Or more words in same row. I mean, it's not a disaster. So then what that means is that you have to search the row. If you don't find it in your first attempt, you go to the next one and the next one. And so you might have to search everything that's stored in table row 7. Okay. But as long as there are no collisions, then you don't have to worry about that. If there are no collisions, okay, then when you go and search for hate, and if it takes you to, row 7 and there's nothing there, it means that no web page has the word hate. On the other hand, if it's in some web page, it'll be in 7. So ideally, we want no collisions. So let's see how we accomplish that. So we want no collisions. And how to accomplish that. So that's what we're going to talk about. But let's have a little bit of a preamble to that discussion. The first is, well, what is this hash function h? Okay. So that's a business. There are people who are spending their entire, research, on constructing good hash functions. Okay. Now, what is a good hash function? A good hash function, well, first, it must be quick to compute. So you want to be able to compute it in constant time for words of a certain fixed length or shorter. Okay. So it has to be quick to compute. Okay. Because otherwise it's going to take you too long to, when you want to search for hurt, to hash it and find out where it is. Okay. And the other thing is that a good hash function more or less takes words and randomly distributes them among table rows. Randomly, independently. In other words, two words that might have, so for example, hurt and hate. They're very similar words, but look, they've gone to way different, table rows. 2 versus 7. And that's indicative of the fact that you can think of this as, hurt is picks a row kind of, at random, and hate picks a row at random independently. So those are the qualities of good hash functions, and we're going to take that for granted. It's someone else's business to give us a good hash function. Okay? So that's fixed in an application. You take some standard hash function and you assume it's a good hash function that has those two properties. It's quick to compute and independently and randomly distributes the words, with equal probability to go into any particular row. Okay? So we don't have control of the hash function. We take a standard hash function. What do we have control over? Well, what we have control over is the number of bins. Okay? Because you can clearly see that if I have more and more and more and more bins, then it's less and less likely that you're going to get a collision. Okay? So let's see how to choose the number of bins. Okay? And that's where the FOCS-twin analysis is going to help us. Okay, so let's compare, hashing with the FOCS-twins scenario. So hashing and FOCS-twins. Okay, so now in hashing you have words W1, W2 up to Wn. Okay, and we're going to hash these into a table. Okay, and in the FOCS-twins scenario, we have students S1, S2 up to Sn, and they have birthdays. Okay. Now, where do we hash? We hash into a table with bins 0, 1, 2 up to 10. Well, in general, 0, 1, 2 up to b minus 1. So bins 0 or table rows. So you hash into table rows 0, 1, 2 up to b minus 1. Okay. And in the FOCS-twins scenario, we are hashing, students are born on days, birthdays born on days 0, 1, 2 up to b minus 1. Okay, so you have b birthdays. Okay, we started them before at 1, but we can start them at 0 and then go up to b minus 1. Okay, and now in the situation of FOCS-twins, we were looking for FOCS-twins. We were interested in the probability of FOCS-twins. Okay, so we had FOCS-twins. So FOCS-twins, we're interested in the situation of no FOCS-twins. Okay, and that's what this formula gave us, the probability of no FOCS-twins. Okay, if you consider student 1, 2, 3, and so on up to k. Okay. And here we're interested in the situation where you don't hash into the same row, no collisions. We can call those hash twins. We're interested in no hash twins. Okay. And the scenario is exactly the same. People are born on random days with equal probability. If the hash function is good, it hashes a word randomly into one of the bins. The same number of analogous situation. Birthdays correspond to rows. Okay. And if the hash function is good, it hashes words independently. And we assume that birthdays are independent. So the setup is exactly the same, where words correspond to student and rows correspond to bins. Okay. And so the probability of no hash twins, the probability of no hash twins, i.e. the probability of no collisions, is exactly equal to, now this is the birthday problem, right? Because we're going to ask none of the words. We want all the words to not have a collision. So we go from, we start with B possible birthdays, B possible rows. So it's B minus 1 over B times B minus 2 over B times B minus 3 over B times, and so on, all the way up to N, B minus N plus 1 over B, okay, times when N equals K, so this term is 1. So the probability of no collisions directly using this formula is exactly this value. Okay. And we want no collisions, so you should choose B enough such that this B large enough, it turns out B large enough such that this probability is large, so that the probability of no collisions is large. Okay, and that happens when B is large. So let's take an example. Supposing you have 10 words. Okay, so N equals 10. Okay, and now let's look at the probability of no collision, so that search will be super efficient. Let's look at the probability of no collision for different table sizes. Okay, so different table sizes. So table size B, and we'll try 10. Okay, so this is equal to N. We'll try 20. This is equal to 2N, and we'll keep going. 30, 40, 50, then we'll go up to 100, then we'll go up to 500, then we'll go up to 1,000. Okay. Various table sizes. Okay. And we're interested in the probability chances of no collision. Okay. And it turns out, so let's see what's the calculation for N equals 10. For N equals 10, what we're going to have is B minus, when B is 10, so we're going to have 9 over 10 times 8 over 10 times 7 over 10 times ... Okay, 1 over 10. Okay. This number is approximately equal to 0.0004. Okay. So the chances of no collision, the chances of no FOCS-twin, the chances of no collision is basically 0.0004. Okay. It's overwhelmingly likely that you will have a collision, at least one collision. And we're being very strict. We want no collision, so that no matter what you search for, it's going to be very efficient. Okay. What about if N equals 20? Now, if N equals 20, this number goes up significantly, 0.07. So there's a 7% chance that when you hash, there'll be no collisions. What about N equals 30? It goes up a lot, it goes up to 18%. Okay. N equals 40, it goes up a lot to 29%. See how it's going up rapidly as you increase the table size? When N equals 50, it goes up to 38%. Okay. N equals 100, we're at 63%. Okay. N equals 500, we're at 91%. And N equals 1,000, we're at 96%. So even with 1,000 rows in your table, okay, it's still the case that there's a 4% chance of some collision. But we want 0 collisions. That's quite strict. Okay. Theorem. Okay. If B is in little omega, remember little omega, growing larger than, if B is in little omega of n squared, So if the table size is slightly larger, rising slightly larger than n squared, then the probability of no collisions goes to 1. So you will have no collisions. That's quite strict. Okay, now this represents a very standard trade-off in computer science, okay, where, what we're after is kind of instant search, and the price we pay for that is a larger table size, n squared. Okay, so as n gets larger and larger, n squared suffices, okay, to give us no collisions with overwhelmingly large probability, close to 1. Okay, so if you give me more memory, I can get you much faster running time. And that's a standard trade-off in computer science. And we see it here with hashing. Now, of course, this can be a very large memory if n is, let's say, 1,000,000 words that you want to hash. Okay, so this may be unbearable. So what you do, you allow some collisions. And you can do this analysis asking what's the probability of, at most 5 collisions, at most 10 collisions. So at most 5 or at most 10 collisions, means that when you get to a table row, you'll have to search at most 10. Okay, that's still a constant. Okay, so you still get nearly instant search. Okay, so that's the application of the birthday paradox and this analysis of independence and coincidence, okay, to hashing. It shows that you can get very efficient search, good hashing if you have large table size and avoid collisions. Avoiding collisions is exactly the birthday problem. So let's erase. We're going to come back and talk about random walks. Okay, so the random walk. Okay, this is a really beautiful application of independence and probability in general. So let me tell you what the scenarios that we're going to analyze. So there's a street, there's a bar, the drunk walks out of the bar, forgot, where home is home left or right. So, and also the guy's drunk and has no short-term memory, nothing. Okay, so the guy, walks left, and then takes a moment to breathe and then walks left or right, or when he comes out of the bar, he could walk right. So basically the drunk walks left or right randomly, okay, with equal probability to go left or right, and he has no memory. Okay, and, in one direction is the jail. If he gets to jail and is that drunk, he's going to be put in jail for the night. In the other direction is home. If he gets to home, he sleeps well. Okay. And so, this is an example of a random walker. The drunk is walking around randomly. You can think about it, you walk out of a bar, you don't know whether your car is left or right, so you might randomly walk around looking for the car. So the question is, what are the chances that you will find your car? What are the chances that this drunk makes it home? So here's the scenario. Okay, so there's a bar, and, the bar is at some position, and then, let's just make a simple example. So here's home. Okay, so here's home, and let me try to draw home. This is my image of the drunk's home, and here's the jail. Okay, so the jail looks something like this. Okay, now, the drunk starts here and can walk right or left, okay, with equal probability, 1/2, 1/2. Okay, and, let's try to see what can happen. So what are the possible sequences for moves of the drunk, that can happen. So if the drunk moves left, he's at home and that's the end. He gets into bed and sleeps. So L. Okay, and what are the chances of that? L is 1/2. Okay. Now he could move right. Okay. He could move right, in which case he's in jail. Okay. And again, the whole process stops and he sleeps in jail for the night. And because of independence, now this is where the independence comes in, because each step is independent, the probability to walk right is 1/2, and the probability to walk right again is 1/2. So we have 1/2 times 1/2 because of independence. You multiply probability, so this is 1/2 squared. What else can happen? Instead of going right, he can go right, left. Okay, and now he's back to the bar, and from here he can either go left, okay, in which case it ends, so right, left, okay, and the probability of this is 1/2 cubed, okay, or he can go right, left, right. So right, left, now he can go right, okay, in which case he's in jail, so that's 1/2 to the 4th, or he can go right, left, so right, left, and he's back at the bar. Then the probability of this is, the chances of this is 1/2. Okay, but now if he's back at the bar, he can go either left, okay, or he can go right, left, right, right. That's another way to end. Okay, so this would be 1/2 to the 5, and this would be 1/2 to the 6. Or you can go right, left, right, left, right, left. Okay, and now he's back at the bar, and he can go left, or right, left, right, left, right, left, right, right. That's another way to end this random walk. Okay, so this would be 1/2 to the 7, and this would be 1/2 to the 9, and so on. These are the possible outcomes for the drunk. Okay. Now we're interested in the probability to make it home. Okay, and so what are the chances of making it home? The chances of making it home are here 1/2. Okay, that's an outcome where he makes it home. Another outcome where he makes it home is right, left, left. So he makes it home left, right, left, left. So right, left, left, he makes it home. Okay, right, left, left. So we can call that right, left, squared left. And he makes it home. Right, left, right, left, right, left, left. So right, left, cubed left. Okay, and in general, any number of right, left moves to some power k, followed by left, brings him home. And those are all the sequences that bring him home. Now let's see what are the probabilities of each of these outcomes. And now we can use independence. This is 1/2. This is 1/2 cubed. This is, there are 5 here. So this is 1/2 to the 5. And this is 1/2 to the 7. This is 1/2 to the 2k plus 1. Okay, and we see that, the probability to make it home, okay, now these are the outcomes where he makes it home, so that defines the event of interest. The probability to make it home is exactly equal to 1/2 plus 1/2 cubed plus 1/2 to the 5 plus 1/2 to the 7 plus, and so on. Okay, so this is the infinite geometric progression again. This is equal to 1/2. So the first term divided by 1 minus the common ratio. The common ratio is 1/4. So 1/2 over 1 minus 1/4, which is equal to 1/2 over 3/4, which is equal to 2/3. So not bad. The drunk will sleep at home. The chances the drunk sleeps at home are approximately 2/3 or 67%, 33% chance of being at jail. Now let me show you another way to get this same answer, but using the law of total probability. Okay, so law of total probability. Interesting. Okay, so law of total probability. We can say that, the probability to make it home. Okay. Now the law of total probability says break it into cases. There are 3 cases. Okay, either he moves right, so it's the probability to make it home, given that he moves. Either he moves left. So the probability to make it home, given that he moves left. Okay, weighted by the probability to move left. Okay, so this is what the law of total probability says. Plus the probability to make it home. Okay, now the walk can start with either right, right, or right, left. So probability to make it home, given that he starts off right, right, times the probability to move right, right, plus the probability to make it home, given that he starts his walk right, left, times the probability to make it, times the probability to start right, left. Okay, and this is what the law of total probability says. Break it into cases. There are 3 cases for how he can start off his walk. Either he moves left, okay, that's one case, or he moves right, right, or right, left. There are no other cases. So you compute these conditional probabilities, weight by the chances of each of the cases. Okay, now comes the interesting part. The probability to make it home, given that he moved left, is 1, because he's already at home. So this is 1. Okay, the probability to make it home, given he moved right, right, is 0. Because he's in jail. So this is 0. Right, right, right. And the probability to make it home, given that he moved right, left, okay, that's the interesting case. If he moved right, left, he's back at the bar. So it's like this process is restarting. The random walk is restarting. And the probability to make it home, if he starts right, left, is exactly the probability to make it home that we're trying to compute. Because the probability to make it home that we're trying to compute is exactly the probability to make it home if you're at the bar. So this is the probability to make it home that we're trying to compute. Okay. So this is going to equal 1 times the probability to move left. That's a half. So it's 1 times a half plus 0 times whatever is 0 plus the probability to make it home times the probability to move right, left. That's a half times a half, independence. So that's a fourth. Okay. And so what we have is that the probability to make it home is equal to 1/2 plus 1/4 times the probability to make it home. Okay, and this is usually the case when you try to analyze such infinite processes that could go on forever, because you could keep on going RL, right, left, right, left, right, left. You could keep on going forever. You get an equation for the quantity you're trying to compute, the probability to make it home, in terms of itself, which you have to solve. So we take this to the other side, probability to make it home times 1 minus 1/4 is equal to 1/2, or the probability to make it home is equal to 1/2 over 1 minus 1/4, exactly what we got before. This is 2/3. Okay. That's, in some sense, much simpler because you don't have to analyze this infinite set of outcomes, and we don't know if we did this correctly, but here, everything is nice and clean. Simple, 2/3, correct, bam. Okay. Now, I'm going to show you an application of the law of of the random walk to gambler's ruin. Okay, so gambler's ruin. Okay, so this is an application of the random walk, almost direct application. Gambler's ruin. So here's what's going on. You're a gambler. Okay, you walk into a casino. You have $2. So you're a poor gambler like me. You only have $2. Okay, and you're going to play a game. Okay, and this game obviously favors the house, but at each step you're going to bet $1, and you can either lose the $1, which means you drop in wealth by $1, or you can win an additional $1 and you increase your wealth by $1. So you start with $2. Okay, and each time you play the game, you can either drop in wealth from 2 to 1, you can increase in wealth from 2 to 3. Okay, that's the ideal situation where you increase in wealth. Okay, and if you're at $1, you can bet your $1, you can either lose, so you have 0, and now you're clearly unhappy. Okay, and we say that you've been ruined. Okay, so that's ruined. On the other hand, if you have $2 and you win, you move up to $3. You bet your $1 again, and if you win, you go up to $4. Now, at some point, you have to decide that you're going to leave the casino. You can't stay here forever. Okay, so obviously, if you get ruined, you have to leave. And we will say that your goal is to double your money. So if you get to $4, you win, you're happy, you leave. Okay, so you're happy, you win, you leave. So in some sense, you're a very disciplined gambler. Okay. Now, of course, real gamblers, once they get to this point, they think they're on a streak, and so let's keep going, let's try to double again. Okay, we'll see that that's a disaster. Okay, now let me show you what's going on. Okay, now clearly, this game is going to favor the house. So, let's say you start with your $2, and essentially what's going on, you either move left or right at each step, okay, with some probability. So let's say that you move left with probability Q, and right with probability P. Okay. Now, in the random walk, the drunk, it was truly random. He walked left or right randomly and independently with probability 1/2. But because this game favors the house, Q will usually be bigger than P. So you're more likely to lose than to win. Okay, so let's set Q equals to 0.6 and P equals to 0.4, just as an example. Okay. Now, the obvious question that we want to know is, what are your chances of winning? What are your chances of doubling up before you get ruined? So what is the probability to win? Or equivalently, what is the probability to lose? To ruin. Okay, now if you think about it, this is exactly the random walk problem, where you can think of ruin as the equivalent of jail and doubling up as the equivalent of home. And we would like to know, if you keep playing this game until you either get ruined or you win, until you double up, what are your chances of reaching, your double up state before you reach the ruined state? Okay, same question here. What are the chances of reaching home before you reach the jail? Okay, and we can analyze in exactly the same way. You can build up the sequences that lead you to ruin or the sequences that lead you to doubling up and add up the probabilities, and it's complicated and tedious. Or you can take the law of total probability approach, and in the text, we analyze the general gambler's ruin problem, okay, where you can imagine that you have some number of dollars and your goal is some higher number of dollars, and you'd like to know what are the chances that you reach your goal before you get ruined. And we can even do this whole analysis for general Q and P. Okay, Q plus P must equal 1. So if you want to see that analysis, read the text. But a very good exercise for you is, for this specific scenario, compute your chances to win, or equivalently compute your chances of ruin, and take 1 minus that, you get your chances to win. I'll just tell you the answer. Okay? We use exactly the same techniques that we used for this smaller example of random walk. This is another random walk, a little bit more complicated because it's got more places to go, and a little more complicated because it's not half. It's PQ. P is 0.4, Q is 0.6. Okay. But your probability, your chances of ruin are approximately 69%. Approximately equal to 69%. Now that's not so surprising. And that's basically what gives the house these odds, right? The house has got better odds than you. And so it's more likely that you get ruined. So you might try to defeat this strategy by saying, I'm going to walk into the casino with more money. So let's say you start with $3. Start with $3. You might think, well, so now my game is as follows. I'm going to do the same thing. I'm starting with $3 and I'm going to play until I either get ruined or double up to 6. What are my chances of ruin? Chances of ruin are equal to approximately 77%. Wow! Your chances of ruin went up if you start with more money. So let's see what happens if you started with $10. So you'll play either till you get ruined or till you double up to 20. Start with $10. Chances of ruin are approximately 98%. Wow! So in this game, trying to double up with $10, okay, you will get ruined 98% of the time. It's truly a gambler's ruin. In fact, when you play this kind of... Okay, now this was for these specific odds, but you can do it for general odds. In fact, when you play this, gambler's ruin game, okay, the more money you start with, the richer you are. The richer you are, so the richer you are, the more likely you are to get ruined. The more likely to get ruined. Wow. It's truly a gambler's ruin. The richer you are, the more likely to get ruined. Okay. So you want to avoid the gambler's ruin. Avoid this kind of a scenario. And you might think, what are other better strategies which give you a better chance of winning as you get richer? Okay, so that's an interesting problem. It all falls within this realm of random walks. Okay, so that's the end of today's lecture. Let's just recap where we are so far. We have mechanical ways of computing probabilities, which are interpreted as how often does the event occur. Then we know how to update probabilities with new information. That's conditional probability. And today we studied how probability gets easier to compute when you can assume independence. Okay, so be on the lookout for independence wherever you are trying to analyze probabilities. It makes computing probabilities much easier because you compute the probability of an AND by multiplying probabilities. Okay, and with that, I'm checking out. Till next time. See you next time.